Hi everyone, yeah, since that's so much fun, another recording. So today I'm going to talk about regularization. Last lecture we talked about deep neural networks and we built our first multi-layer perceptrons, and we've seen if we have a lot of parameters, it can happen that we overfit when we do the training. So that basically means we train our model on the training set and then we observe that the accuracy goes up and up and up and up. But at some point we see a decline in the validation performance, and also the test set performance in the end will not be as great due to overfitting. So that means the model may remember or memorize certain things in the training set that are not general. So the methods or the predictions don't generalize to new data. And in deep learning, or in general in machine learning, the whole goal is basically to make good predictions on new data. So in order to prevent this overfitting, there are different techniques. Usually they are summarized under the umbrella term regularization. So one classic technique for regularization is just stopping the training early. So if we observe that the validation set performance goes down, we can just stop training it. That would be one classic technique. Another set of classic techniques is L2 and L1 regularization, so weight penalties. So in that way we add a penalty against complexity. So one of these you have already probably heard about in other statistics courses. For example, L1 regularization is also known as lasso regression. The other popular one is L2 regression. So in that way the L2 penalty adds a quadratic penalty to the loss function. This is also known as rich regression, if you've heard of this. And these are also two, I would say, not too common techniques anymore in the context of deep learning. So one really popular technique that has been developed around 2013, 2014 is dropout. And we will talk about dropout also in this course, which is maybe right now the most, I would say, frequently used and well-used technique. So let me do the screen swapping again, and then let's go through the lectures. Okay, 1 second, there we go. So yeah, today we'll be talking about regularization, which is a technique to prevent overfitting. So last time we looked a little bit what overfitting is, how it looks like on different data sets. So overfitting, why it's a problem is because our model may just memorize certain patterns in the training set which are not generalizing to new data, which will mean basically that our model will not perform very well on new data. And how we can reduce overfitting is, for example, by reducing the model capacity. Last lecture we talked a little bit about model capacity, what that means. You can think of it in simple terms as just the number or the complexity of the model, how complex the decision boundary can be, so what types of functions the model can approximate. So we can basically reduce the rate of overfitting by reducing the capacity of the model, making the model simpler essentially, and also by reducing, this is kind of tied together, by reducing the variance of the predictions. So if we think back of last lecture, we took, for example, the mean squared error and we decomposed it into a bias, variance, and noise term. So by reducing the variance, we can also reduce overfitting. By reducing the variance, that basically means that we if we look at different training sets, we would produce similar or consistent predictions when we fit a model on different training sets from the same population. If we have a high variance, if there are slight changes in the data set, in the training set, the outputs, the predictions will be vastly different on the same test data point. So a variance here means how different the predictions are if I trained the model on different training sets that are still from the same population but have slight differences. So how sensitive is the model to different patterns of noise in the training set? So this is a problem that we want to suppress. So this overfitting is something that is not desirable. So one way to reduce overfitting is by regularization. So regularization techniques also lead to the lower capacity that I just previously mentioned. In the context of deep learning, you can also just in more general terms think of regularization as adding additional information to the training procedure. So to add some sort of constraint, you can think of it as a change to the objective function, for example, some additional information. So, and this regularization can help us with reducing overfitting by, for example, reducing capacity of the model. So the common regularization techniques that are often used in deep learning are early stopping. That means stopping the training early before, or when we see a decline in the validation performance, before it gets too bad, we stop the training, because then we avoid that the model overfits too much. A better way to address overfitting is adding a penalty to the loss function, for example, L1 or L2 penalties. These are the common norm penalties, which add a coefficient or a term that is depending on the size of the weights to the loss function, and by that we will reduce the size of the weights, which means that the model will be less sensitive to small fluctuations in the data set. The third technique here would be dropout. Dropout is maybe the most popular technique in deep learning for reducing the model capacity or just preventing overfitting. So we will talk about these topics one by one, but before we even go to the early stopping, I just wanted to give you another brief tip how to get better performance and how to reduce overfitting. That would be simply by collecting more data or augmenting the data that you already have. So that is an additional point. I wouldn't call this regularization, but it is also a very useful technique to prevent overfitting. So I would generally, if you can, always recommend collecting more data. So the more data you have, usually the better the model will perform. And it is also helpful, for example, if you have image data, to modify your data. So it is not always possible. So for example, if you have image data, for example, let me lay down my iPad here. So one possible way to augment the image data is by adding random rotation. 1 second here, let me rearrange things. Okay, random rotation would be one way you can augment your data set if you have images. For example, if you think of the MNIST data set, let's say I have my MNIST image, this is the number 2 here. I can, for example, rotate it slightly to the right, so my number is maybe something like this now, and I can also similarly rotate it to the left side, so it's maybe like this. So in that way I can, from one image, so I rotate it here to the right and I rotate it here to the left, I can generate additional training data points that are very similar to my training set. However, these are new data points and can help with overfitting, because now the model can't exactly memorize the pixel positions. For example, let's say we have this original image here on the left. I have a pixel, use a black color here, pixel in this position. It may just remember, okay, there are 2 pixels here at these positions, and if there are 2 pixels here at these positions, then it's the number 2. However, if I now slightly rotate it, so this pixel may still be the same position, but this one, the previous pixel, is now here. So it can't really memorize the exact position of the pixels, so it has to somewhat learn a pattern or more like an overall shape. That is one way for augmenting images. However, you don't want to do something maybe completely crazy. It depends, of course, on your application, but you maybe don't want to completely rotate your image. That may not always make sense. So there are certain, ways where this may make sense. For example, if you build an ATM machine and you want the machine to read the numbers, whether the check is upside down or not, that makes maybe sense, but it wouldn't make sense really to mirror images. In that sense, if you have numbers, for example, if you think, some space left here, if you have the number 2 here, you don't want to, it's hard to draw a mirror to, you don't want to flip it basically, because this is something you wouldn't encounter in real life, so this is not like a real number. So in that way, you have to be also a little bit careful about what types of modifications you consider. For example, for face images, it may not make a huge difference whether you flip the face or not. That makes maybe sense, because it depends how your camera works. Some cameras produce mirror images, some don't. So in that way, maybe that is something that's okay. But you don't want to create like these weird numbers by flipping numbers. Other ways how you can generate artificial data points is, for example, by cropping. So cropping. That means simply that if we have another number here, say this is our original MNIST image, what I can do is I can resize my image. I can make it a little bit larger, for example, like this. And then I can crop out a random region from this image that has the same size as the purple region. So let's assume it's the same size. I can crop a random region. And this is basically equivalent to just translating the number of pixels to a different position. So this has the same effect as if I would have put the number 2 here. So but this resizing and cropping trick is computationally a little bit cheaper than computer, so just moving the pixels over. So that is one way you can do this. But you can also, of course, crop it in a way that you get a smaller image, a smaller random image. So that would be another way you can augment your data set. Of course, this doesn't really make sense with other types of data sets. If you have text, there's not much you can crop, but there are also certain things you can do with text. For example, maybe introducing some typos, maybe changing a single letter in a text or something like this with a certain probability, or also the capitalization of letters. You can maybe randomly capitalize the letter or not. But that also, again, depends on whether your model uses uppercase, lowercase information. And this is always something you have to think about in a case-by-case basis. For some data sets, it makes sense, and for some data sets, it doesn't make sense. But let's go back maybe to the first term. Collecting more data is always a good idea. So, I mean, it does not always help a lot, but usually it also can't hurt you. So if you can, it's usually always recommended. And one way to find out whether it really benefits you is by plotting a so-called learning curve. So this is called learning curve. What a learning curve is basically a plot that plots the accuracy for different training set sizes. So here what I was doing, I was taking the MNIST dataset, but only a subset because it took a little bit longer to compute on my computer. And just to show you an example, so this is a very small subset of MNIST. What I did here is I have a constant size test set. So I keep the test set size constant. I have to admit I forgot the number, but I think it was 5K. It doesn't really matter. I'm just showing you a constant test set. And then what I'm doing is I'm increasing the training set size. So I start with a very small training set size. Could be, I think it was like, what I said here was 100. And then I'm increasing it up to 3,500. And I can see here when I increase my data set size, so my training performance goes down. So this is, you've already seen this, a softmax model. This is a softmax regression. If you remember, this is like multinomial logistic regression. It's logistic regression for multiple classes. So if you remember how it looked like, it was something like this. Everything was connected to everything. So it's a linear model, a generalized linear model. This is, the inputs are the number of pixels in the image. If we have MNIST, it's 28 times 28, it should be 84 input pixels. And the number of classes here, this is, so say C is the number of classes, it's 10 because we have the digits 0 to 9. So we have 10 different digits. It is a little bit weird that the training performance goes down. I mean, this is a generalized linear model. Usually training performance would also go up. It doesn't really matter here. For this plot, the training accuracy really doesn't matter. It's just something you can ignore. However, what you can see here, that's the most important part in this figure, is that the test set performance goes up. That means if I would collect more data, for example, if I would collect 4,000 or 5,000 data points, what I would expect is that this would, maybe not so steep, but it would still go up. So in a way it tells me this will help me collecting more data, would help me getting a better accuracy if I collect more data. Usually also this prevents overfitting. So I'm not sure, I think this is because it's just a generalized linear model, but the cats and dogs example I showed you last time, it would be more something like where we have a training set that starts here, and then usually over time the performance gets better also. But then also you get this increased overfitting rate. But even though the overfitting is bigger here, let's say, than here, you also want to care about the overall performance. For example, if I have this threshold here, you can see even though in this part I'm overfitting more than here, still get a better performance compared to before here. So in that way, it's usually a sweet spot between improving the overall performance versus reducing overfitting. But we'll see another example of that later with the cats and dogs example. Okay. So here are some examples for augmenting images. So at the top, this is the original MNIST dataset. So you can see, I mean, this is just 28 times 28, so it's a little bit pixelated. But 784, it's already a big data set still. So if you think about images that we work with, if you take a camera picture, it's, I don't know what the resolutions are these days, but let's say 1000 times 1000, you have already 1 million pixels. So it's a huge data set, so it's easy to overfit. In this lecture, we are just working with multi-layer perceptrons just to keep things simple. After spring break, actually, we will talk about convolutional neural networks, which are models that can deal with such data much, much, much better. In any case, just to focus on data augmentation for now. So I'm showing you an example here of the MNIST dataset, just 4 random numbers or data points. So here I have a randomly augmented version of these images. And I should mention the augmentation is random. So every time I run this, it will do something that is slightly different within a certain range. For example, I can say, rotate my image in a range between, let's say, -20 and 20 degrees. So it is always a number between those two. It's not always the same number. This is kind of useful because it allows us to almost create infinitely many versions of that image. Also, one more thing I wanted to say here is I have 2 versions of this. So there's this randomly augmented version and this randomly augmented version. Here, the big difference is that in the middle row, I'm just using, at the bottom row, I'm just using the default settings, and you can see this 2 and this 1, they are, or even, this is very extreme, in the 9, you can see it's more pixelated than this one. It may be a good or a bad thing, but I think this is maybe a little bit too extreme. This is just how function of how this rotation method works. So if you want to get a little bit better quality, there is in the Python imaging library this bilinear filter that you can, or interpolation method, sorry, that's a interpolation method. This will help you to get a little bit better results. So in the center row, I was actually using this PIL image bilinear thing to get a little bit of a better performance. If you want to get the code examples for that, it's all on GitHub. I don't want to really go there because it's kind of boring. I don't want to just execute the code because there's not much to see. So I just made a screenshot of the relevant part, which is the transformation. So in PyTorch, there is this Torch, or Torch Vision is kind of part of PyTorch. It's a separate Python library. But if you went to the python.org website, maybe let's just do this. It's maybe easier to show. So when you, if you already installed PyTorch, which I think you already have because you needed it already for homework, I recommended you to select the installation command based on your computer, of course. And let's say you selected, let's say you have a Mac computer and you selected the Conda one, Python version with CUDA 10.1, or it could also be just no GPU. it will give you a command here that already, if you have seen that, it will already include Torch Vision. So chances are you have it already installed, so you don't have to worry about installing it separately. Since we are already in the browser, we can actually go to GitHub here. And then our class repository. And we are talking about regularization. This is the code, data augmentation. So this is not very exciting code here. So all I'm doing is I'm importing the Torch Vision packages. So I'm actually importing two things, Torch Vision and Torch Vision datasets. So in the dataset sublibrary, they have some datasets available, like MNIST, so you don't have to download it manually. So it's providing you some functions to load that more conveniently. That's mostly for benchmarking. However, in the project, you will likely work with your own dataset. And for that, you need to use your own data loader methods. But homework 3 explains you or shows you an example of how to load an own dataset that is not part of this datasets library. But I'm getting distracted here again. So let me talk about Torch Vision and not the datasets for now. So what I'm showing you here is two transform methods. So I'm building my own transformation pipelines using Torch Vision, maybe a little bit bigger, Torch Vision.transforms.compose, and the compose method lets me compose number of rotations, a number of transformations, whatever I like, and they have a lot of options there in this library. I'm just showing you some of them, but if you go to this website, they have a whole range of things. Let me see. Probably added a lot more recently. So there are a lot of different methods. Maybe helpful to just scroll through this and see what kinds of things they have here. But the major ones I would say is random rotation, resizing, and random cropping. There's one method, random affine, that does multiple things in one. So this is the one that I've shown you in the slide. And always, so these are methods that are executed on PIL, Python Imaging Library image format. So here the data is still in an image format. However, for PyTorch, we need to get that into a tensor, a PyTorch tensor. So this is what this method is doing. It will convert the image into a tensor. One side effect that I sometimes forget in the beginning, when 2017, when I was using other tools and then PyTorch was new, and I was sometimes over normalizing things, because one thing to keep in mind about this is it's already scaling the data into a 0-1 range. I don't know why they do that. Maybe it's just, I don't know. Anyways, so it is an automatically normalizing, min-max scaling the data into the 0-1 range if you execute this toTensor command. For image data, it's always, or in general, it's helpful to have data centered at 0, so that you have small positive and small negative values. That's because you also have the weights usually centered at 0, and it just, we will talk more about this, it will help optimization. So here what I'm doing is I'm also normalizing my images such that they are centered at 0 and will be in the -1 range. So let me go actually back to the slides, because then I can. Okay. So going back, oops, that's maybe a little too far. So going back to the slide here, just to again show you what's going on here. So this is just a screenshot of what I've shown you just in the browser. So at the top, I have my training transformation. And at the bottom, this is what I'm using for the test set. So for the training, we have this random affine, but this is just really a convenience function wrapping all these three together. And here's some randomness. So we have these random modifications, whereas in the test set, we have deterministic behavior. But again, back to the normalization here. This is the z-score. So one more thing is, this is just called normalize, but it is called z-score normalization, which is basically what we know as standardization from the previous machine learning class in standardization. And what it is doing is it's basically rescaling our data such that it has zero mean and unit variance. So this is usually helpful because then our data will be centered at 0. It can have small positive and small negative values, similar to how we initialize weights. Weights are also initialized such that they have small positive and negative values. And this usually helps optimization algorithms, and we will talk more about optimization algorithms in the next lectures. Here what we are doing is we are rescaling it with these properties such that if we use, so maybe I should write down the operation. So x prime assume is the modified or rescaled training data point, and we rescale the given data point. This is actually also for a given feature. So let's say this is for pixel I, the ith pixel. Shouldn't have, okay, this. We subtract the mean first, and the mean is computed as the average over all images in the training set for this pixel location, for pixel I. And then we do the same thing for the standard deviation. Again, the standard deviation is computed over the whole training set. And this is for the ith pixel. So this is how we standardize a given pixel. And if we do that, after the standardization, the pixel position will be across all training points, be centered at 0 with unit variance. And why? So in this case, actually, what will happen is that the range will be -1 to 1. So normally, if you have a data set, you have the spread, the standard deviation, so it can be usually values larger than -1 or values, smaller, more negative than -1 or larger than 1. Here, it is bounded by -1 and 1 though, because we already normalized images using this normalize function here. So why is that? Why is it -1 to 1? I mean, this is just easy to see. Let us plug in some numbers here. So if I consider this equation here, or this formula here, and then I plug in for the mean the -0.5. I'm taking it from here, so I'm plugging this in here. And in my denominator, I also put the 0.5, which is coming from here. And then for the pixel, I put in, the pixel numbers could be between 0 and 1. So let's put in a 0 here first. And 0 minus 0.5 is -0.5 divided by 0.5. This would be -1. And if I have, so let me write on the left corner here. If I have pixel value 1, I subtract 0.5. Then I divide by 0.5. This would be 0.5 divided by 0.5, which is 1. So in this, this is why the boundary for the values is between -1 and 1. In this special case, this is just a side effect of this normalize function. Also, I should mention in practice, these values are derived from the training set. So in practice, we would compute the mean and the standard deviation from the training set. This is like the, I would say, most correct way to do this, but it honestly doesn't really matter in terms of the network performance. If you choose constants, it's usually fine. If you look at, later we will do that at transfer learning methods for pre-trained models available, let's say in Torch Vision, you will find for ImageNet, they estimate numbers like for 0.4 something. So it's usually pretty close to 0.5, but of course it depends on the data set. But it doesn't really matter here. And also here, just for simplicity, we use 0.5. Let me clear the screen here a little bit because too much drawing here. There's one more thing I want to say. And this thing I want to say is that we put one value here and one value here for the mean and the standard deviation. And this is because MNIST is a black and white data set or grayscale data set. So if we have the dimensions of, so let us write it like this. So this is a matrix of real values. Each image is a 20 by 28 times 28 matrix, but we also have a color channel. So it's usually a 3D tensor, so 1 by times 28 times 28 tensor. So the 1 here stands for the color channel. So here we only have one color channel here, which is why we only have one mean and one standard deviation. So we compute them usually separately for each channel. And here, what we are doing is we are putting in a tuple. However, if we would have a data set that has multiple color channels or multiple, let me see. So if we have a data set with multiple color channels, for example, RGB, we would have 3, for example, in this case, this would be 3 color channels. So we would also have 3 mean values and 3 standard deviation errors if we standardize by color channel, which is what's very common for images. If you have a tabular data set, you would actually normalize this by a feature value by each column in the data set. So here we are normalizing by each color channel, so we can have a different mean and different standard deviation. Okay, so one more thing, I'm seeing this here at the bottom. This is actually very important. So you've already seen that we have data loaders in PyTorch, and for the data loader we provide a data set. And the data set is just a class, the dataset class, that defines how a data point or image can be opened in PyTorch. Here we use something that is already in Torch Vision, this dataset subpackage, where there is already an MNIST dataset contained. And all we have to do then for the data loader is to provide the training dataset, and for the training dataset, or for the dataset in general, we have an optional transform method or a chain of transformation commands, and these are our commands that perform this data augmentation. So these are the different ones that we define, and we just provide these transformations to the transform argument here, and then it will apply all these transformations for us. So now this is for the training set. If I have a validation or a test set, for example, let's assume this is the test set, I would also just change this to test transforms, which are these here, basically. So that's all we need to handle training and test sets separately. And it looks maybe a little bit confusing. I was doing a lot of drawing here, but it's super simple in practice. As you see in homework 3, it's actually not a big deal. It's pretty easy to do. Let me go to the next slide then. If there are no questions, but haha, you can't ask questions. No, you can ask questions on Piazza, and we'll have office hours, so you can ask more questions. Because this is like a little bit unfortunate that we don't have this interactivity here, so we have to rely on other methods for asking questions. I will also maybe make some smaller quizzes to see if you, if everything was clear, or maybe what parts need more explanations. Okay, next slide. Okay, so here I'm just again letting you know for RGB images you want to put 3 numbers in here because you now have 3 color channels. So we talked, what time is it? Maybe we talked like almost an hour about data augmentation, but the real lecture is about regularization. So you're reducing the network capacity and early stopping. That's the simplest part about the simplest method of regularization. So we are entering now the part 2 here, where we talk about reducing the network capacity. So one way to reduce the network capacity is simply to choose a smaller architecture, so making the network smaller, using smaller hidden layers, using fewer neurons, and also adding fewer hidden layers. So the simpler the architecture, the fewer parameters you have, and the fewer, or the lower the chance that you will overfit. Another way, so this will be one way to decrease the capacity of the network. The other one is to enforce smaller weights. The L2 penalty, for example, is one common method. You probably heard about this in the context of other statistics classes. There's a method called rich regression, which adds a penalty to the objective function, and this makes the weights smaller, basically. We will see how this works in detail. Another way to reduce the capacity and enforce smaller weights is early stopping. So it is a little bit unintuitive. Why does it enforce smaller weights? I mean, it's just more like an intuition that it can enforce smaller weights, because if you train your network, your weights get updated all the time, so they go in either direction. And if you train it over fewer epochs, there are fewer updates, and you can maybe hypothesize the fewer updates you have, the smaller the magnitude of the weight, so because you don't push it into these extreme regions. But of course, it also depends on the learning rate and many other things. And also, it does not mean that you have always a small weight. What it does, though, if you have, let's draw it like this, if you have your, let's say, accuracy here, and this is your number of epochs. So if you have so let's draw the training set performance. Let's say it goes like this. This is for training. And then for the test set performance or validation set performance, you will see it will start maybe here, and then you will see it goes maybe not quite as high, and then at some point it may even go down. So this is for the validation. So we maybe want to stop at some point. I mean, this is something where you have to run the network to really see how the method performs, but then maybe this would be a good stopping point here. At this epoch, you would stop the training. So you would run the whole network, but imagine you just saved checkpoints of your model. You would reload this model, and then you can evaluate it on the test set after that. So you hypothesize, here's a small overfitting, it's overall good performance, and this is, you hypothesize maybe the best model in this range here. Okay, that would be one method for reducing the capacity. And the last one, maybe the most popular one, is the dropout method. So to, again, start or go back to the early stopping principle, I think I actually wanted to explain this with a few slides. I was going a little bit ahead and was drawing something. But again, let's go through this slowly. So what you do is, and I would always recommend that, you take your data set and divide it into 3 parts. So you have a training set, a validation set, and a test set. How big should these parts be? I mean, this is kind of a little bit arbitrary. Depends also on the overall size of your data set, but usually it's, I would say, a good recommendation to use something like 80% for training, or maybe I would say 15% for testing and 5% for validation. Validation is maybe the least important part. I mean, all of them are, of course, important, but the more data you have for training, as you've seen earlier when I showed the MNIST softmax plot, the more data you have for training, usually the better for the model. And you also don't want to have a very small test set, because you want to have, so the test set is gives you an unbiased estimate of the generalization performance, but of course it can also have a high variance. So you want to, you can have fluctuations basically depending on what data point ends up in the training set and in the test set. And a larger test set will essentially give you a more reliable estimate of the generalization performance. So you want to have a relatively large test set, so also people believe your results when you, let's say, write a paper. But you don't want to waste too many, because then your training set will be too small and then the model will not be good. So it's in practice a trade-off. You want to have as much data as possible for training, but also you want to have a relatively large test set, so your estimate of the performance will be somewhat reliable. Yeah, so you divide your data set into 3 parts, and the training set is for the model fitting, so you fit the weights and bias units based on this training set here. And the validation set is something you use during training to estimate the performance already during training. But of course, you will experiment with different hyperparameter settings. You will change the learning rate. You will change maybe the architecture. You will change the number of epochs, activation functions, and what have you. So if you use the validation set every time to evaluate the model, you kind of leak information into this procedure. So in that way, because you reuse the validation set, it will not be an unbiased estimate of your test set anymore. This is kind of somewhat related to hypothesis testing when you do a hypothesis test multiple times until you, let's say, find a p-value that is smaller than your desired significance threshold. At some point, if you test on the same data set multiple, so if you conduct multiple tests, at each test, I mean, how t-tests work, for example, is you have a probability of observing the data given the null hypothesis, so that there's no effect. If you repeatedly, so with this, usually you set a significance level of alpha 0.05. So you have a 5% chance that you observe a value that is extreme as the observed one, the data, or more extreme 5% of the time. So you have a type 1 error of 5%, but you inflate the error if you do multiple tests, basically. Also, the more tests you do, so you can think of it like this. If you have this 5% error rate, the chance that you don't make an error is 0.95. And now assume you test something 7 times. So you do 7 hypothesis tests. So the chance that you don't make a type 1 error is this number. I can't compute this in my head here right now, but it could be 0.7, I don't know. So yeah, and then the chance that you make at least one error, that you are wrong at least 1 out of the 7 times, is then simply 1 minus this value. I don't know what number this is. Can't do the math right now in my head, but let's assume this is some number between, I don't know, could be 20, 30. Let's just go with 25. We'll check after this lecture. I was probably super off, but there's, let's say, a certain. Don't take this with a grain of salt, but there's a certain chance, a higher chance that you make a mistake if you do something multiple times. And this is somewhat, I mean, what we are doing here is not a hypothesis test. But it's basically the same issue, that if we test multiple times, we increase the chance that we just select something just due to chance. So the validation set is not super reliable in terms of the true performance of the model, the generalization performance on all possible data, but it is a pretty good guess. So this guess is actually better than the training set performance guess, because from the training set, we can't really tell whether something is memorizing, the model is memorizing data or not. The validation set, it's not used for training, not for fitting these weights and biases, so it's somewhat more unbiased, but it's not totally unbiased because we use it for model selection, we use it for hyperparameter tuning, and we use it multiple times, which is why it's always important to have a separate test set. Okay, so here I have a plot again. So this is actually what I've drawn before. So this is a plot that shows you the accuracy for different epochs, so increasing number of epochs. And you will see usually that the training set performance will go up over time, and the validation set performance will usually go down. There will usually be a point. At that point, you will see that you get the maximum validation set performance, but then you will see the performance will go down. And usually this point where before it goes down is a good point to stop. And again, so here, the overfitting is less than here. However, we are maybe still more interested in this point because it has the highest overall performance in terms of the validation set performance. I'm not showing you a test set performance here, but my guess would be a test set performance. It would be usually a little bit lower than the validation set performance. Because like I said, the validation set is a little bit biased because we select our models based on the validation set. So sometimes it's just like, we are lucky that we get a good performance on the validation set, and we select the model specifically on the validation set. So on the test set, it may not achieve that good performance as on the validation set. Okay, that is early stopping and maybe the simplest technique for overfitting. However, I mean, this is not a bad idea, but we will look now at different methods that help us to kind of shrink this overfitting range. So if I go back and clear this slide a little bit. Okay. So the methods we are going to use, they will try to shrink this region that is the overfitting here. What will happen? So our goal is to have a validation set performance that is maybe somewhat like this, closer to the training set. But of course, it will not always be perfect, but we will aim to reduce that. One danger with that, though, is if we reduce this overfitting too much, if we are too strong with our regularization, what will happen is that we will decrease both the training set and validation set performance. So what we may see is training set performance is now something like that, and the validation set performance is maybe, it's not overfitting that much, as you can see, but it is overall, let's make this straightest line here. Overall, it's lower than before. So we don't want to add a very, very strong regularization, because then both the training set and validation set performance will not be as good anymore. However, we want to also still reduce this gap. So we just hope that the validation set performance without overfitting is now better than with overfitting. So one way to achieve this is with adding norm penalties to the loss. So there's L1 and L2 regularization. So how that works, you probably have heard about this from other statistics courses. So there is a Lasser regression, and this is the L1 penalty. And there is rich regression, which is the L2 penalty. So these are both methods that we sometimes also call weight shrinkage or penalty against complexity. That simply means that we keep the weights small, and with small weights the decision boundary will be simpler, because then there are less, so input data points have less influence on the decision boundary, because remember, when we compute the net input, so we usually have an activation function which takes in some value. Let's call this value z, and z itself is computed by the weighted sum of the inputs. So we have usually the weights, let's say in a generalized linear model, or in general we have, let's write this properly. So we have our training set and then our weight matrix. So here we have a weighted sum. Let's also add the bias vector. So weighted sum, and if we keep the weights small, the decision boundary will be less susceptible to small changes in X, for instance. So in that way, we have a simpler decision boundary if we have smaller weight values, especially if some weight values are close to 0 or even 0, then these weight values don't play a role at all. And that will again lead to a smaller or simpler model and a smaller model complexity, because fewer weights play a role in determining the prediction. Yeah, okay. So how this works is that we simply add a term to the loss function. This is the term for L2 regularization, which helps us to reduce the size of the weights. And at the top, I'm showing you the cost or loss function in general. So sometimes I use this terminology that call the loss on a single data point L or loss. And if I speak or talk about all training points, all n data points, I called it the cost. The cost is basically the averaged loss over all data points over the whole training set. Y hat is as usual my prediction, and Y is my true class label. And this depends on what model we use. It could be the mean squared error that we had. This could be the MSE. Or it could be the negative log likelihood. Doesn't really matter. So the same concept applies to both the mean squared error, negative log likelihood, or cross entropy. It's the same thing. So it could be some arbitrary loss function. And what we do now is we add this L2 term. And the L2 term is simply, so here let's imagine a generalized linear model like logistic regression. So these are my inputs, and then I have something like that. that gives me my y hat. So these are my axes, and there are some weights, and there's, let's draw an additional bias unit. So this is my linear model. So I have these weights, the weight vector. So the weight vector contains here j weights. So let's go W1, W2, W3, up to Wj. And so, sorry, this is, let's say we have m weights, and this is, if I pick one of them, it's the jth weight. So we have m weights. So what we simply do is we square and sum up the weights. So this is writing, this is equivalent to W transpose W, just squaring all up these terms, and then having this lambda coefficient. So this lambda coefficient is just arbitrary hyperparameter. So I wrote this actually here. So this is a hyperparameter that determines the strength of the regularization. Of course, the larger this lambda parameter is, the larger this term becomes. So large lambda means like a large penalty term. And I'm also averaging over the number of training points because I'm also doing this in the loss function. You don't have to do that. So you can actually cancel this one and this one. So the mean squared error will become the sum squared error. But usually I like adding these averaging terms here because it makes the training more stable. For example, if you change the mini batch size, you don't have to recalibrate the learning rate that much because because what we do is when we compute the gradient updates, we have an update that is W plus the negative gradient times, or we can also subtract the gradient, times the learning rate, so the loss gradient with respect to one weight. So if we do that, we usually choose the learning rate. Let's call this learning rate eta, or sometimes we also say alpha, doesn't really matter. So for this learning rate here, we have to choose this carefully to converge. And since this is a multiplicative factor, it is, if I have this 1/2 here, this 1/2 will also appear in my derivative, in my loss derivative. So if I have, what it basically means is if I have more data points here, because of the sum, the loss will, or the cost will be larger when I have a larger mini batch size. And if I have a larger cost, then I have to reduce the learning rate. So every time I change my mini batch size, I would have to fine tune my learning rate again. Of course, you always should fine tune the learning rate if you make changes. However, it's simpler, it's more stable if you have this averaging term. Then it's less susceptible to changes in the mini batch size. What I wanted to say here is, yeah, so we have this squared term here. I think I may have not even mentioned that. So that means this whole term will become bigger. This whole term that we add to the loss function here, this whole term will become bigger as the weights become bigger, because this is sum over the squared weights. So it will become quadratically bigger with the larger weights. Let me clear again the slides because it's getting messy here. So the bigger the weights, the bigger this term becomes. And if this term becomes bigger, the weights become bigger, then also the whole cost, or let's just call it loss, becomes bigger. And again, remember, our goal is to minimize the loss. So in order to minimize the loss, we have to minimize two terms now. We have to minimize the prediction performance, so how close we are to the true label. But then also we want to minimize the second term, which is the size of the weights. So ideally, we want to have this 0, because then this won't affect the loss. But if we have a 0 weights, I mean, it will be likely that this will be a very bad prediction, because y hat depends on the prediction, where this is again, well, let's try like this, WT x plus bias. So If we have a zero weight, we'll have a very small penalty for the size of the weights, actually zero. But then again, our predictions will probably not be good. So there should be a sweet spot. We want to minimize the prediction error, but also at the same time, we want to minimize the weights. So we want to minimize two things now. So that is L2 regularization. L1 regularization is pretty similar. The only difference is that instead of using a squared term here, so we in squared size of the weight, we use the absolute value here. We won't go into too much details here of what it does exactly. So there are lots of books and papers written about that, about lasso regression. So here, or in general, the key idea is that it encourages sparsity, and sparsity means that many values in the weight vector can become zero. So the stronger the regularization, the higher the chance that you will have, or the higher the number of zero weights. So so L2 regularization just shrinks the weights, and this will, in addition, force the weights to be zero. So you can think of it, it can be useful for feature selection even. So you select features using lasso regression, but you cannot choose which weights become zero. So it's also kind of limited if you have, so you can't choose the number and which weights become zero. So in that way, it's not really the same as feature selection, but it is it can be useful to reduce the complexity of your data set. So if you have a weight vector, the weight has let's say W1, W2, let's say we have 4 weights in this weight vector. There's a high chance with lasso regularization that, let's say, 2 of them become zero. And if it's just convention in computer science, we say, or in general, we say if linear algebra, if more than half of the elements in a vector or matrix are zeros, then this is a sparse matrix or a sparse vector. But of course, this is just a loose convention. What sparsity essentially means is that there are many zeros. And L1 regularization encourages many zeros. The one advantage, of course, is disadvantage is, of course, this is not differentiable. So with the L2 regularization, so again, when we do our gradient descent, we want to compute the gradient, which we use then to update the weights. If we have now a modified cost function or loss function, but we also have to differentiate. So let me go back here, maybe a second. Okay. Okay, so what I wanted to say is, so what we usually do is we compute partial derivative of the loss with respect to the weight to update the weights with gradient descent. Before we were just computing the derivative of the loss function, for example, the derivative of the mean squared error. Now we have to add this penalty term. We also have to derive that. And if you probably know, it's the simplest rule in calculus, the sum rule. So if we have a function, let's say composition of two, not a composition, a sum of two functions. Let's call one maybe gx. So if we want to derive this one, we just derive them separately. So it's the sum rule. So in that way, what I'm trying to say is we can just derive this term separately and add it to the derivative of whatever this is, depends on the loss function. In order to compute the derivative for this part, I mean, it's pretty simple. We use the power rule. We just bring this one forward. So it's 2 lambda over n, and then sum over w. That's basically it, right? Do I miss something? No. So this would be basically our simple penalty term that we add. And this is nicely differentiable because it's just square. That's not so nice here because we have an absolute value now. Of course, we can use tricks like the one that we use for the relu function, but I would just say this is usually a little bit harder to optimize because it's not like a smooth function, like a quadratic function. And So with a quadratic function, again, we have, let's say, some value. Let's call this P for penalty or something like this, size of the weights. So what we'll have in L2 regularization, something like this. And in L1 regularization, we will have something like this. So it won't be that smooth to optimize. And yeah, talking about this, I think I added some slides to explain you more behind the intuition. Yeah, I did. So here there's some quick geometric interpretation of L2 regularization. So here what I'm drawing is a surface plot. So there are two axes, W1 and Wi and Wj, and these are both two arbitrary weights. Just assume I have a linear model, generalized linear model, the logistic regression, or let's say even add a line with a linear activation function. So this is, I have multiple weights, so each connection is a weight, and I'm just picking two of them. So let's say I pick this one and this one. So I have my Wi and my Wj here. And in the surface plot, this is the contours represent the loss. So this point here in the center, this is the minimum loss. So this is where the loss is the minimum value. That's the point that we want to get when we optimize the loss term. When we optimize, let's say 1 over n. Let's just not do the 1 over n, just for one data. Oh, maybe it's better. Okay, so if we want to minimize this term, the loss or cost, then if this is minimized, we are here in the center point of the surface plot, and the further we go outside, the larger this value becomes. So before, this was our regular optimization objective. Now in addition to that, we have this penalty term, which is what was it, lambda, and then the sum over the squared weights. So we have this additional term, and this becomes larger the larger the weights become. So I'm showing you the second term via this second contour graph, and the penalty or loss will be exactly 0 for that weight if. So this is the gray shaded area is the loss for the second term, and it will be 0 if the weights are 0, because then we have a sum over 0, which is 0 basically. So in that way, so that would be if we are at 0. So that would be the optimal for the weight penalty. That would be optimal value. We minimize the second term. However, if we minimize the second term, we have 0 value here, but we are very, very far away usually from the minimum loss value, this part. And again, if I go back 2 slides, so we want to minimize this thing and this thing. So, and there's a sweet spot. So if I only minimize this thing, then usually this other thing will be large. So we have to find the sweet spot. And it turns out for L2 regularization, this sweet spot is, of course, makes sense. It's usually somewhere in between. And it will be usually a weight that is smaller than the weight that we would get without the penalty. So you can see this is more to the left. So it's crawled here. So here we have a relatively large weights, and if we are in this sweet spot, the weights are a little bit smaller. So the axes again are representing the sizes of the weights. And this is just a geometric interpretation of this. So we want to find a good sweet spot between having small weights, but also minimizing the loss function. This is for L2 regularization. For L1 regularization, this looks relatively similar, but now we have this diamond shaped thing. The same concept applies. We want to find a sweet spot between minimizing the loss and minimizing the size of the weights. However, it turns out that often the compromise will lie on one of these axes. So it will lie either here or here. And if that happens, one weight will be here, in this case 0. So that is the main difference between the two. So this one will encourage like these 0 weights. What's next? Okay, so I was talking about generalized linear models, logistic regression, and so forth. Of course, though, we work with multi-layer neural networks. So what we have is, the difference is basically here we have a matrix now. It's a weight matrix. So before we had a weight vector. So matrix consisting of, let me draw it like this. We usually have m columns, where m is the number of features in the previous layer, and then we have, how shall I call this? Let's call this h, the number of values in the next layer. So then usually what we do is we have our, this is our training data set. So this is usually n times m, and then we multiply it by W transpose. And then this is our weighted inputs and so forth. So we have this weight matrix now, so there are multiple weights, and in how we use weight matrix for regularization, it's pretty simple. We just use the Frobenius norm, which is just summing the weights over the columns and the rows. And we do this actually for each layer. That's all we need. Okay, so here I have also what I already drawn that before, the update for grain descent. So here it's for one data point. So the only difference I have here is that so this is for one particular weight, sorry. So if I have it shown for one weight, I and j. So this is one, so if I have my weight matrix, this is one weight in the weight matrix. So if I update this again, regularly I subtract the loss with respect to that weight times the learning rate eta. And now when I perform my update with the L2 regularization, I add this penalty term and actually the derivative of this penalty term. This is pretty simple. It's like I said before. So if our penalty was I j squared and then lambda 2 n. So, oops, that's correct. So just for one weight. So we just simply update this by using the power rule. So we bring the 2 here, and this is all we have to do. It's a quadratic term. It's pretty simple to derive, and then we just add this to our loss function, and we apply the learning rate to both of them, and this is all we need. So how does it look like in PyTorch? So here I'm going to show you 3 ways now to do regularization in PyTorch. So there's L2 regularization for logistic regression, doing it manually, then doing it automatically, and then I think I have a third one where I do this for neural networks. So let's go through it one by one. Okay, so in this first one, let me open this. Okay, this is the code notebook. I just clicked on the link in the slides, and this is a very simple notebook I prepared to compare logistic regression with L2 regularization, doing it manually and doing it automatically. I did it both ways, so you can see that both produce the same results. For instance, here I have the weight parameters after regularization, which are 1.7546 and 1.5997. And if you go down a little bit, the automatic, so this was the automatic way, sorry. It gives you these parameters, and the manual way, it gave you the same parameters. So just to double check that my manual approach is actually doing what it is supposed to be doing. Okay, let's not scroll around too much here and go through it step by step. So in this notebook, I'm simply loading a very basic, simple, super simple data set. Doesn't really matter because I just want to get some results to see that regularization is implemented correctly. So this is a very simple logistic regression model for binary classification. I just have one layer, because logistic regression we don't have hidden layers. It's just a layer connecting the features to the output. There's only one output in a logistic regression. Again, this is just to zero the weights and biases. It's not really necessary, but since it's a convex cost function, we don't really need to start with random weights. And then we also only have our single sigmoid activation. That is all something that you've seen before. It's nothing new. The new part here is in the training. So what I'm doing here, so I'm showing you the automatic way. So what I'm doing here is implementing logistic regression with regularization. And like I mentioned before, L2 regularization is much more popular in deep learning compared to L1 regularization. So there is a dedicated parameter of the optimizer. There is the SGD, the stochastic gradient descent optimizer, that we used before, and it has a weight decay parameter. And the weight decay parameter is actually implementing L2 regularization. And here we simply provide the lambda term, the regularization strength, and what value this should have. I mean, this is hard to say. It depends on the data set, depends on the model and the model capacity. And usually this is something you have to find out via hyperparameter tuning. Maybe you want to start with 0.5 and then see whether making it larger or smaller has a beneficial impact on the overfitting rate. So reducing overfitting by addressing or changing lambda. But then also you want to see that the validation accuracy doesn't go much, doesn't become too bad either. So like I said before, there's usually also a sweet spot, finding a spot where you have moderate regularization, that the training accuracy and validation accuracy remain high, but that you also reduce the overfitting. And that is all we need to do. So I have my binary cross entropy here, and that's it. There's no further change required. Let me maybe go through the slides though, because there I can draw here. It's a little bit hard to explain things just by highlighting it. Let me go back to the slides. So the slides, I was just simply copying sections from the notebook. I was just showing. Oops, no. Okay. I'm sorry. It's always when you do things live. Okay, so I was showing you things for the automatic approach where we have this weight decay parameter function argument in the SGD optimizer, and with that it will automatically perform the regularization for us, which is exactly equivalent to doing it manually this way. This is what I had in the notebook as well. Section, so the lower section of how to do this in the manual way. What I'm doing again is I'm computing the cross entropy, the binary cross entropy for logistic regression. Again, remember this is the negative log likelihood. And here I'm just computing the penalty term. When you remember, the penalty term was for regularization was this lambda over n and then w j for the jth weight, and this is the penalty term. So here though, one thing I should say is I'm using the sum of the loss function, so I'm not using the average. So here I specifically said sum, so in that way there is no averaging going on. So all there is, it's just a summation of all the weight terms, which is being done here. So this is W transpose W. So what it will do is we'll just compute the weighted sum of all the weights. So if I have a weight vector that consists of, let's say, W1, W2, W3, what it will do is simply compute W1 squared plus W2 squared plus W3 squared. So I'm just computing with this dot product here, I'm computing the weighted, basically the quadratic terms summed up. multiplied by my regularization strength lambda, which is maybe a value between 0.5. I have to check in my notebook what I actually chose there, but doesn't really matter. Another thing I have here is the 0.5 coefficient. Where does that one come from? If we go back, here. Okay, so when we go back here, this is my regularization term. And like I said, we use, when we compute the derivative, we just use the power rule. We bring the 2 up front here. So it's actually 2 times lambda over n sum j w j. Okay, so here the 2 will go away. So the thing is, it may be a little bit annoying to have this 2. So you have 2 times lambda. It can be confusing. So in that way, usually we add a 0.5 in front of it. So instead of writing it like this, some computational tools assume you have written it as this, and then the squared. So what will happen then is, if you use the power rule, you put the 2 here, then it will cancel each other. So you have this one and this one cancels. So that is actually what's going on in PyTorch. So PyTorch does this by default, and this, if I go back, this is basically the 1 over n. 1 over 2, sorry, which is the 0.5 that we are seeing right here. This is, so like I said, I wanted to reproduce the results that PyTorch does or give us automatically. So I have to do this if I want to get the exact same results as with the automatic approach, but it's not really necessary. Another aspect is that PyTorch is regularizing the bias unit as well. So in order to reproduce the results, you also have to consider this bias term. In PyTorch, the bias is just treated like a regular weight. This is fine if you use deep neural networks. It's a little bit weird though for generalized linear models. It's not really ideal. So if you want to implement logistic regression with PyTorch, I recommend maybe not using the automatic way, doing the manual way, and then also getting rid of this term. Or if you use PyTorch to implement linear regression, regularized linear regression, for example, rich regression. The reason why we don't want this is if the bias is regularized, you lose the intercept. And I mean, this is fine if you standardize your data with mean 0, but if you have not, then this can be a problem. For example, think of a regular linear regression for now. So let's say I have my target variable in linear regression and some dependent variable, my predictor variable or my feature variable x. And then let's say between the target and the features, the data points look like that. So as you know, the bias unit is the intercept, the y-axis intercept. So if I have a linear regression model, I may fit the data like this. Just imagine this would be a super straight line. But now let's assume I regularize the bias. What will happen is that the bias will be also becoming smaller, forced towards 0. So what will happen then is, if my bias goes to 0, so if I move it this way, what will happen is something like this should be a straight line, sorry. It will look like this maybe, because it kind of forces the bias to be 0 or close to 0, and then can't really fit this data well anymore. So in that way, this is why we don't want to regularize the bias. We don't want to really change the intercept. But again, if you standardize your data, so if you have exactly the same data and you use this z-score standardization, normalization, which was like this, x prime, x minus the mean divided by the standard deviation. If I do this to the data set on the left, what will happen is their points will be centered at 0 somewhere, and then I don't need this intercept term. So in that way, I don't care whether the bias is regularized or not, because it will be 0 anyway. But in general, I think it's most of the time a good idea not to regularize the bias. In PyTorch they do this. It doesn't matter for deep neural networks, but for simpler models like linear regression or lasso regression or rich regression, it would matter. Okay. So this is if you do it manually. This is just implementing the equations that we have talked through. And if I do this in PyTorch again, I use this weight decay parameter and set it to lambda. Okay. Yeah, so this is a question for you. Why is the bias usually not regularized? Which I think I just explained to you, so that is a pretty easy question, but yeah, still doesn't hurt to ask yourself the same question before the final exam. Maybe it is a question in the final exam, who knows? So now I'm showing you regularization for a neural network that has more than, so that has one or more hidden layers. That is where we use the Frobenius norm. This is, again, super simple to implement. This is very similar to before, except that we have a weight matrix. So what I'm actually doing, instead of going over the rows and columns, I'm applying this regularization to all model parameters, which is the weights and the biases, like PyTorch does. Just summing them up. And one more thing is, what I'm also doing here is I divide by n. So the targets.size 0, this is n, number of data points in my mini batch or training set, depends on what the features is. If this is a mini batch, it is a mini batch, so n is the mini batch size. So this is then exactly like the equations we had on the previous slides, and this is required now because I'm not setting reduction to sum. So I'm not setting it to sum. And by default, if this is not set to sum, it's the average. So this is why I'm also applying this n here. Anything else interesting here? No, I mean, this is exactly the same as before, except now that we have a weight matrix instead of a weight vector. I just iterate over all the parameters because it's just simpler to express in code. Okay. Oh, I just answered this question already for you. So the targets.size is just the 1 over n. And like I said before, in neural networks, it doesn't really matter whether we regularize the bias or not. But if you really don't want to regularize the bias, then you can also do it like this. It's a small modification. So here, instead of before, I was just iterating over all parameters. Now I'm iterating through something like a named parameter list, so or dictionary. So here I access the parameters by name, and so this is a tuple or dictionary where you have a name and then the parameter value itself. P is still the parameter value. Name is now a name like bias or weight, and I'm just checking whether the name contains the word weight, so whether it's a weight or not. And if it is a weight, then I apply my regularization again. So this is exactly the same as before, except that I'm now specifically only choosing the weights and not the biases. Just quickly here. So yeah, how it would look like. I mean, this is really exaggerated. So just assume you have a model with a very strong and a very weak and a moderate regularization strength. And this is really exaggerated, so it won't look that extreme, but assume you have a data set like here in the center, and you have low regularization or no regularization. So in this, what will happen is that your decision boundary will be relatively complicated. So what it means is it's very complicated in shape, so it is fitting the data very closely. I'm writing high variance here because if I would have a slightly different training set, so if I would have, for example, the training set, let's say, just maybe shifted a little bit like this, the decision boundary would look different. It would look maybe like this. So in that way, it's very susceptible to how the training set looks like. If I would sample from the same population though, so then if I have a model that has a strong regularization, So for example, here on the left-hand side now, this one has a very, very simple decision boundary. But then, of course, the downside of that is that it has a very high bias. So last lecture, we discussed bias and variance. So, but what it means also, if the regularization is strong, it will also have likely have a low variance. What will happen is that even if the data set is maybe a little bit shifted, so let's say I shift this a little bit to the left, this also, and maybe this also, maybe it will shift the decision boundary a little bit like this, but it won't have such a strong effect as this one. So small perturbations in the training set don't have such a huge influence on the decision boundary now. But this again has a high bias, so this is also not good. I mean, if you look at this one, it still gets 100% of the cases right in the training set, which is good. Here, this is maybe too simple, so we get this data point wrong. So it's maybe not, I mean, it's not terrible, but it's not great either. So maybe a good compromise between the two would be a model that has slightly higher capacity. For example, this one here on the right. So here we have a decision boundary that is somewhat compromised between the super complex and the super simple decision boundary. And this is what we want to find usually. So this gets, again, 100% accuracy on this training set. And we think maybe also on a validation set, this may perform well. Of course, it's not guaranteed, but the one in the center is likely fitting the data too closely. It's maybe not necessary to fit the data that closely. Okay, let me take a sip of water here, because it's been pretty, I think, long. I think maybe 1.5 hours here, but we are going to finish this. So I'm planning to make one video per lecture, so it's not split up into multiple videos. I hope it's all saved on my computer. Okay, so the last topic for today is dropout. So like I said before, dropout is maybe the most popular regularization methods for deep neural networks. It's also one of the newer ones. I mean, right now it's already 2020, so it's 6 years ago. But in deep learning terms, 6 years is a long time. But I would still call this relatively recent. I mean, given that it's a regularization technique. I don't know any other recent methods that are commonly used as well. I mean, this is still one of the state-of-the-art regularization methods. So if you want to find out more, I'm only covering some overall aspects about dropout. If you want to find out more about the details, I would recommend reading this paper. There are actually 2 papers related to this. So these 2 papers are good references if you want to learn about dropout. I think the main paper is more like the 2014 paper, but there's already some early concepts explained in the 2012 paper. And yeah, so like I said, dropout is not a super complicated method. It's useful, but if you think what it's really doing, I can summarize this in one slide, which is this one. So what dropout is doing is it's just dropping out weights or connections. Actually, it's not dropping out weights, but really the activations. So imagine you have a multi-layer perceptron, like I'm showing you here. What it will do is with a certain randomly it will, with a certain probability, remove neurons here. That means it will remove, in a way, the weights that are coming in and things that are coming out of this node. So it will simply just zero that node. So this will be zeroed and this will be zeroed. But this is again random. And this selection of activations to drop change in every forward pass. So that means, so they are also not updated during backpropagation, of course. So in each forward pass with a certain probability, a given activation is dropped. And that means also, so this is specific only during training. So for example, in each mini batch, this might look different. So in one mini batch, I may drop the ones that I am showing you with the red crosses here. But in a different mini batch, now assume all of them are active. In a different mini batch, it's maybe this node and maybe even this node, and then this node. So it changes every forward pass. And I will briefly show you or explain why this might be useful. But Yeah, so, but the overall concept is just dropping nodes. What I have here on, I was just looking what I wrote here on the right corner. Because I always, you probably noticed, there's a lot of text on my slides, and that is because it's, I thought, useful for you, so you have some notes. Usually when I give presentations, I don't have any text on the slides, but then it's not useful for studying, I think. Anyways, so the probability with the probability, some space here. So the drop probability is usually around 50%. So 50% is the one that they recommended in the original paper. But in practice, it could be any value between 0.2 and 0.8. And also, one thing to mention is you don't want to drop out anything in your output layer, of course. So the probability can range between 0.2 and 0.8. It is again a hyperparameter. There's no way of knowing for sure what a good value is without trying. Of course, the higher the dropout probability, the higher the regularization. But yeah, this is just one parameter. If you have no clue what dropout you want to use, you maybe don't want to even start with 0.5, but maybe 0.2, so you don't drop out too many, and then you can go from maybe 0.2 to 0.8 and see how that affects your network. So a little bit more, I would say, concise what's going on. So what dropout is basically doing is like a Bernoulli sampling, but only during training. So it's only going on during training. So what we do is we define a dropout or drop probability. So that's the probability with which activation gets dropped. And in order to implement the dropping itself, we first draw a random sample from a uniform distribution in the range between 0 and 1. So imagine I have my activations. Say my activation vector, so this is, let's say, one layer in my network. Let's say I have A1, A2, A3, A4, A5. And I want to drop about 50% of them. Or let's say I want to drop 40%. So that means, or let me go back and do 10 activations, so it's easier to talk about it if we have a nice number here. Oops, what happened? So I have these 10 activations, and let's set this 60%. So we want to drop 60%. So if we have 10, I mean, this is like a random number, but let's just say 6 out of 10 are ones that are being dropped. But of course, each one is dropped with a 60% probability. So we first would draw this vector v, which is a random sampling from a uniform distribution in the range between 0 and 1. So this will give us a vector v. And this will be some numbers, say 0.1, 0.8, 0.2, and so forth. And what will happen to that one is, so we will apply just, it's similar to the NumPy where we will apply a condition and check whether a value in this vector is greater than p or not. Just seeing, this should be a 1. Okay, so what we do is we apply this condition if v is greater or smaller than p. So if v1, a value in this v vector, is smaller than p, where p is 0.6 for the 60%, then we will set it to 0. So we will set it to 0. Otherwise, we will set it to 1. So what will happen is based on these values. For example, this value here will be set to 0. This value will be set to 1. So we set to 0 and so forth. So we end up with a binary array. So the binary array may look like something like this. Okay. This is random, but it may look like this once we apply this threshold function. And then what we simply do is we multiply, element-wise multiplication, we multiply the activations with this mask. So you can think of v as a mask vector that is only zeros and ones. If we do that, then all the ones that are zeroed out, they are kind of deactivated. So this one, and this one. And if I use my 0.6, 60%, the expected value for this was 60% will be deactivated of these activations, and then only 40% remain. So right now I'm 1, 2, 3, 4, 5. Let's deactivate one more. So we have, let's say, 6 out of 10 are deactivated, and that is all we do. And why do we do this weird Bernoulli sampling? Because it's just one way to implement this. There's no really, I mean, you can just, with the random probability, just draw activation, but this is a simple way of implementing this in code. If you would translate this directly to code, it is super simply to implement, because there are simple uniform distributions also in the PyTorch.random sublibrary that you can just use. Okay. Oh yeah, one more thing is after training we are scaling the activations. So did I show it to you here? No. So we are scaling after training the activations during testing. So in deep learning we also call the prediction phase inference, which goes back to some old AI approaches of unifying logic and statistics. So in that way it's a little bit weird to call it inference, but inference means making predictions in deep learning. It's just a convention we have to get used to. It's maybe a little bit weird if you took other statistics classes, but just go with it. Okay, so when we do after training, when we make predictions, when we predict new class labels for new data points, we have to scale our activations, and that is if we because if we dropped 60%, so p equals 0.6 during the training, we only have 40% of the activations left. So the activations will be 60% lower than in during the testing. So if you just think of all the activations as positive values, let's say from a sigmoid function or something like that, then what you have is, so again, you have the weighted inputs. So the weighted inputs to a given layer, this would be the way, if X is our input data, that would be the activations of our first layer. But in general, you have the weighted activations from the previous layer. And we usually, I mean, there are multiple activation functions, but let's say you use the sigmoid function, so all of them are positive values. If you eliminate, so you eliminate half of them, then your output will also, so if I eliminate half of my activations, I will have also only half of, so it's the same as scaling z by 0.5. Now if I have eliminated 60%, I only have 0.4 or 40% of the activations left. So if I go back, so I have 1, 2, 3, 4, 6, 7, 8, 9, 10. Okay, so I eliminated 1, 2, 3, 4, 5, 6. So I only have 40% left. And all my network is geared, the decision boundary is geared towards these values during training, because that's what we train it on. Now, if we don't apply dropout during testing, what will happen is that our activations will be way too large. So also for testing, we have to decrease the value for the weights. So here we only have our 40% left. So also what we want to do during testing, we also only want to have 40% of the activation. Otherwise, it would be a little bit weird if we have a decision boundary that is trained on a specific threshold, because again, we usually in deep learning, we have a threshold function. And if now everything is lower, we also have to lower it during testing. So what we do is simply, we multiply the activations during testing by 1 minus p. So for instance, if we have during training the dropout probability of 60%, we will drop 60% of the values, 40% remain, so this would be the remaining 40%. So what we do is simply also during testing, we multiply by 1 minus 0.6, which is 0.4, so to get the same magnitude during testing. So yeah, again, so going back here to this slide, what happens in Dropout is we are just dropping half of the activations during training, but not during testing. And why does it work well? So why is Dropout useful at all? I mean, you can think of it because every time in each forward pass we drop out different neurons, you can think of it as a way of making the network less relying on particular connections. Because if we drop connections randomly, it cannot rely on a single or a specific connection to be present in each time. So if you think about the MNIST dataset where we have numbers and pixels, so it cannot just rely for each class, the number, to be in a certain, or to have a certain pixel activated for this class, because the connection may disappear during training. So it has to at least rely on multiple pixels at the same time. So in that way it's harder to overfit, because it cannot just memorize pixel positions, because sometimes the pixel position is present, sometimes not. So it has to consider different locations and different locations at the same time. So what will also happen is that the weights will be a little bit smaller, because it cannot just rely on a certain weight to be present. It has to consider multiple weights. So in that way, the weights will be on average a little bit smaller, because it has to consider more of them for the decision boundary. And this is then also why it is kind of a form of regularization, because we kind of also shrink the weights a little bit. We add some information during training, or not information, but we kind of influence the objective function. Yeah, and we also can use, that's what I have here as a side note, we can also use different dropout probabilities. We don't have to use the 0.5 or 0.6 in each layer. We can just change them. We can, for example, use a high dropout probability in earlier layers and a smaller dropout probability in later layers, for example. I have an optional section here. When I made the slides, I thought it's something I won't ask you on the exam, but let's briefly talk about this. Why not? So I was just giving you an intuition of how Dropout works, but there's also more, I would say, interpretation of Dropout that is based on ensemble and model ensembles. So we talked more about model ensembling last fall semester in the regular machine learning class. You don't really need to know the details of that, but if you're interested, I have lecture notes here. And this is all based on the fact that it's based on the fact that if we use model ensembles, on average, we expect this to get a better performance than just a randomly selected model. For example, what I've done here, I mean, this is just a very simple illustration. That's maybe a little bit confusing, but what I'm saying here is that if I look at the squared error, instead of, so y hat I is a, y hat is a prediction and I is a particular model. Let's say I have an ensemble of n models. So let's say I have models I to n, and here I'm picking just one particular model. And if I look at the expected value, or the expectation for picking one particular model and computing the error for that one, so y is the ground truth, the true label, and this is the squared error for that. So if I look at if I pick out one model at random and I look at the squared error, this squared error is higher than compared to, for example, using an ensemble. So an ensemble, what I mean is the average over all the predictions from the I models. So again, I think, yeah, this is the expectations over the models I. So if I look at the expectation over the models I here, this is also, if you look at this, this is the bias term. Sorry, this is the variance. This is the variance term. This is the bias squared of the mean squared error. So we decomposed the squared error last lecture, or 2 lectures ago. So this is again just the squared error with a bias squared, the variance. I'm not showing you the noise term here, just for simplicity. But all I'm going to say here, or what I want to say is basically that this term is smaller than this term, right? Because this is one part. There's a second part, the bias term. So this one, the variance, is smaller than the arrow. So if I use model ensemble, I will have a smaller model ensemble is beneficial compared to picking one particular model at each time. Yeah, that is just a small, very quick motivation of why ensemble methods are useful. So how is that related to, how is model ensembling related to dropout? So in Dropout, we use a different modeling for each mini batch. Like I said, we are dropping weights randomly. In each forward pass, we drop a random selection of activations. So what we are basically doing is, if we have H hidden units in a hidden layer, so we have H units, we have, let's say, a network, like this. And just quickly connecting this one. So the number of units here, let's assume this is H. So in each forward pass, it will be a different combination of these. So we have, so basically it's like Bernoulli trial. It's either present or not. So we have activation active or not. And what we have is then 2, because it's either present or not, 2 states to the power of H, because we have H different units. So this is 2 to the power of H is the number of different combinations of hidden layers or models we have. So M equals 2 to the power of H. So we have M different models that we can sample from. So each forward pass is sampling from the M different models, from the distribution of all different models. And the only so this is an ensemble of size M. The only difference to, for example, an ensemble method that is based on majority voting is that we have not independent models. The models are dependent on each other because they share weights with each other. Sorry. Talking for such a long time, I need a break maybe, but I'm almost done here with this lecture. So what we have is models that share their weights with each other, because if I have a model, let me say model, just call it model 1, and I train it on my training set or my mini batch, then I do a weight update. And then the weight update is this is my model 2 now, the one with the updated weights. And then I again give it another mini batch. Let's call this mini batch 1 and mini batch 2. So in each iteration, I have a model that depends on the previous model. So they are, in the way, it's sharing the weight from the previous model, or the updated previous model. So there is some connection between these models. They are not independent models. So then what we can do is so each iteration the model changes, we have new weights. During inference or doing predictions, we could technically average over all these different models. However, this would be very expensive. So if you have, let's say, 100 epochs, and you have 1,000 mini batches, so that would lead to 100 times 1,000. 1,000. This would be 100,000 different models. And if you think about it, one model can have already millions of parameters. That would be super huge to store them all. So it's kind of infeasible to store all these models. So there's a simple trick to do this more efficiently, to average over these models. But before we get there, so averaging this model or these models is simply similar to computing the geometric mean. So what I'm drawing here is the goal here is to average over all these models so that we have an ensemble, that we can take advantage of the ensemble. The question now is, how do we average? So we can compute the arithmetic mean. However, it would make more sense because each model, if we think about the output, it's a probability of class membership. For example, you can think of, it's not exactly like this, but let's say it's the probability of a class label y given x, the features. So the output is a probability between 0 and 1. And instead of computing the arithmetic mean, we want to compute the geometric mean. This is basically the same as averaging the log likelihoods. So here I'm just averaging over these different probabilities for one probability for each model, for the ith model. And I would also say I would do that. I'm not showing it here for some reason. I would also say this is for one particular class. So if I want to compute a probability for one particular class, I would average over all the predictions for all the models, M models. J is maybe a little bit unfortunate because I'm also using J here. Let me use K maybe. Okay, so I'm doing that, and then this should be actually an I, because I have I here. Okay, let me change this. Okay, so we are averaging over all the I models, I to M, by just averaging the log likelihoods. It's simpler to compute. So here on the right-hand side, I just applied the log function. So if I apply a log to something, the exponent goes in front of here. And then to scale back the log, I have the exponential term. So I'm just writing this like this. So we have a sum. It's actually simpler to compute than the multiplication. It's numerically more stable. And it's also just for the analogy, it's just averaging log likelihoods here. So that is equivalent to computing the geometric mean, which you have probably done in other classes before. It's usually useful if you compute a rolling average and things like that. Yeah, one more thing is when we have multiple classes though. So if I compute the probability over my model ensemble here, what will happen is that if I do this for each class, the probabilities may not sum up to 1. And if I have mutually exclusive classes, this would be a little bit weird. So for example, if I have my iris flowers, when I have iris setosa, versicolor, and virginica. So there are 3 different flower species. And if a flower is a setosa flower, it cannot be a virginica flower at the same time. It's either or. So what I want is the probabilities to sum up to 1. For example, I can have maybe 25%, 25%, and maybe 50% or something like that. So, but if I use compute the geometric average, it may not sum up to 1. So for example, I have maybe 30% here. So I have a total 105%, which is kind of weird. So that is why we also want to normalize the outputs, the average, the geometric averages. So for that, we can simply use scaling function here. So to normalize them that they are summing up to 1. That is pretty intuitive, I guess. Anything else I want to say here? So yeah, this is our average of averaging over the models. But again, like I said, the difficult or downside here, the computationally difficult part is that we have to memorize all these M models. So that would be very expensive in practice because we would have to save all M models if we want to make a prediction. So there's one trick, and the trick is simply what you've seen before. We multiply by this coefficient, so we don't save any of these models. We just save the last model and scale the predictions by 1 minus p. And this will approximate the geometric mean. If you want to see the details, Geoff Hinton and his colleagues, they have written about this in more detail in their paper. So instead of computing the geometric mean explicitly, we approximate the geometric mean. So if I go back here. So what I have here at the bottom, this is approximating the geometric mean by just using the last model and then scaling during testing the activations by 1 minus p. So this is an approximation, and this approximation is actually the same as the geometric mean if this is a linear model. Of course, we have nonlinear neural networks, so it's not exactly the same, but it's pretty close, and it's just way more efficient. So this is why Dropout is also related to model ensembling, because we can think of it as a way of considering the geometric mean of multiple models to get more robust predictions compared to a single model. Okay, one more thing is most frameworks implement a version of Dropout that is called inverted dropout. So inverted dropout simply means that we scale the activation during training and not during testing. Why do we do that? If you think about, let's say you have a big company, you are Google, and you have 1 billion customers. You train maybe your model that does prediction, let's say your search engine, you train it once, and then you never have to worry about training it again. Let's say, I mean, of course they update the model, but let's just assume they trained the model once, but then they are applying the same model, or they're using it for billions of customers each day, and every little bit of extra computation is super expensive. There was actually a very interesting article a few years ago that they changed the Google logo. They made it a little bit simpler. So they used vector graphics instead of, I think, an image file to make it simpler. And the reason is simply they save some computing power by making a simpler logo if you use vector graphics, because then there are fewer lines or lines of the vector graphic code that you have to write and the browser has to execute. And that saves them I don't know how much, but it saves them a significant amount of money, because every time a user accesses it, you save some electricity, basically. In the same way, you save kind of some electricity if you don't do this multiplication during, or this scaling during testing. It's just imagine you have billions of customers and you don't have to scale each time. That makes a difference if you have billion freer computations each day. So in inverted dropout, what we do is we scale during training. So we just apply this factor during training instead of testing. So once we trained our model with dropout, we don't have to worry about it during testing. And yeah, most, for example, PyTorch dropout, most tools also, I think TensorFlow, they all implement this version of inverted dropout. How it looks like in practice, so this is Dropout in practice. I also have the code examples in our GitHub repository. Using Dropout is super simple. So I'm again showing you different ways to use it. This is the functional way, so functional API. There's also the more object-oriented way to do this. It doesn't really matter how you do it. But yeah, this is just showing you an example of how to do it the functional way. So what's usually useful is to define a parameter, drop probability. So it's a probability that you drop a certain activation or unit in the hidden layer. And this is what we had previously as P, the drop probability. And so in PyTorch, there is already in this functional, so I still get questions from some students what F is. So F is import, from PyTorch.nn. Oh, sorry, this was actually correct. Okay, it has been a long lecture. Sorry, I make mistakes here. Import PyTorch nn. Okay. Functional as F. So the F is just a shortcut for nn.functional. And so I don't have to write this whole thing every time, so I can just use the letter F. So I'm using this functional version of Dropout from PyTorch, and it's very simple to use. All I need to do is to put it here wherever I want to have a dropout after layer. So this is one layer. This is this computes the net input. This is the activation, and then I apply dropout to the activation. And how this works is I provide the activation value, and then I provide this probability to drop out a certain activation. So for example, 50%, 50-50 chance that this gets dropped. And I also, this is very important, I provide this parameter for this training parameter, the argument self.training. And this is so self.training is the value true or false. So this is just a value that indicates whether the model is in training mode or in testing mode. And this is why it's important, if you think back of our Jupyter notebooks, I mentioned this previously, we sometimes, or not sometimes, actually in every epoch, we have some code that is this code. This sets the model to training mode. If we execute this, then what happens is model.training, this is an attribute, this will be true. So let's just write it like this. It will set it to true if we execute this. Then there is a related method. This is called, I'll write it now on the left side. There's model.eval. And if I execute this one, then model.training will be false. So by setting this, I can indicate by executing model.eval or model.train whether the model is in evaluation mode or training mode. Eval stands for evaluation, basically prediction mode or inference mode. So this is very important because, like we said before, we want to scale so we use inverted dropout. We want to scale the values during training, but not during testing then. So in that way, we make sure that dropout is only applied, the scaling is only applied during training, and also the dropping is only applied during training. In testing, we don't want to drop any nodes. We want to have deterministic behavior. So during testing, we don't want dropout. And if this here, if this self.training is false, then the whole dropout will be disabled. So then we make sure that dropout is only applied during training, which is why, again, model eval and model train is super important when you use dropout. It's actually crucial. Okay, this is the more object-oriented API. So it's doing exactly the same thing I've done before, except that I use, that you have seen before, the sequential approach here. With this sequential approach, I just put the object-oriented version, the dropout class here. And for this one, what is nice, I don't need to manually set this training here. So I don't have to specify training equals self.training. It will do it automatically for us. So actually, if you have more complicated models with a lot of things going on, it's actually more convenient to use the sequential API, to be honest. Okay, so this is doing exactly the same thing. So this is one layer, then I have dropout. And then I have another layer, and then I have again dropout, and then my final output layer where I don't have dropout. And that's it. Here I'm just showing you again that it's important to set the model to training and eval. So I mean, you don't have to put it exactly in this position, but I like to do this. So in each epoch, you set the model first to training mode. And then if you compute something like the test accuracy, you don't need you don't want the dropout. If you compute accuracy, you want to have deterministic behavior. So you set the model to evaluation mode. And again, this no grad just means that I don't want to compute the gradient during testing because I just want to compute the accuracy. And it would be wasteful to compute the gradient because it's very expensive. It builds this computational graph in the background, and it will also build a super huge computational graph if we compute the accuracy because we don't apply the backward method, which deletes basically the graph in the background. So it's always important to set also the no grad here. Okay. So here's an example of using dropout. So this is on GitHub. I don't think I really have to go to GitHub now. It's already been a long lecture here. So just if you want to check this out, this is code implementing Dropout like I've shown you in the previous slides. And on the left-hand side, I'm showing you a model without Dropout. So this is no Dropout, and this is with Dropout. Okay, so what we can see here on the left-hand side, we are overfitting after some time. So on the x-axis are the epochs. So we can see maybe at epoch 25, it starts overfitting. So you can see the gap between the training and validation accuracy becomes larger. And the black solid line, that is the test accuracy. So the test accuracy I computed it at the end. So I just edited this here to the slide to show you the test accuracy. And the test accuracy is very similar to the validation accuracy. It's also because I didn't really do hyperparameter tuning. But if you do a lot of hyperparameter tuning, you will see that the test accuracy is usually not as good as the validation performance, because the validation set has been kind of selected based on the hyperparameters, and you sometimes just get lucky that you choose hyperparameters that are doing extremely well on the validation set. So yeah, here you have the overfitting going on, and if I add Dropout to it, I think I added 0.5, like 50%, then you can see that it reduces the overfitting, so there is no gap between validation and training set anymore. However, maybe this Dropout is a little bit too strong, because you can see also that the performance of the model is not as good anymore. So this one is maybe, how to say, maybe 95.5 or something like that. This is maybe more like 97% here on the left side. So you can see I'm kind of maybe regularizing too much, because now both the training and validation accuracy are lower than before. So this is also why you have to do some tuning when you use a Dropout. So it's not always good to add a lot of Dropout, but in general, it is helpful. So if your model does not overfit, I mean, there's no need to use Dropout. It's only useful if your model does overfit. It is recommended, though, by also the authors of the Dropout method, that you make a model that has higher capacity than you need and that overfits, and then use Dropout compared to using a simple model without Dropout. So it's usually a good idea to make a network that is too large and then add Dropout to it, compared to making a small network to begin with. There's a special, or more, not a special, a generalized version, I would say, of Dropout. It's called Drop Connect. So in Dropout, we drop the activations, which means that we drop the incoming and outcoming weights. In Drop Connect, what we do is we actually drop the weights. So each weight has a probability to be dropped. So this is more like a general form of Dropout. So Dropout and Dropout and Drop Connect would be the same if, for example, let's say, if I would drop this node, in Dropout it's the same as in Drop Connect, dropping this weight, and these 4 weights here. So in that way, it's more, Drop Connect is more like a general term. In practice, I haven't really seen any person really using that. So this is from 2013. Maybe when it was new, some people used it, but I haven't really seen that in practice. I think it doesn't really do so well in practice. So usually Dropout is still the preferred method. Okay, so that was a super long lecture. I need a break before making the next one. So just for you, a reading assignment, because it doesn't hurt. I think you are already bored at home probably. So this paper from that was initially presenting Dropout is maybe a nice one to read as background material. And yeah, this was a long lecture. Hopefully it was somewhat clear what I said here. Downside is since it's a recording, you can't interrupt with questions, and it was longer than usual, so I'm a little bit tired, to be honest. But if you have questions, please go to Piazza, to the forum, and I will make a post on Piazza after I uploaded this video, so you can just directly comment on Piazza about this video. And we will have also, after spring break, digital office hours. We will have some time where we do a video chat. I will set it up via Google Hangouts, so then also you can ask questions about the lecture. Yeah, so that's it. I will be back with the next lecture soon. Bye bye.